Welcome back to another video. So in the last video, we introduced the concept of state machine in VHDL through the use of the case statement. We did two examples. I think we designed the basic counter and then we designed the up counter with a small twist that the up counter had an external input, which we have to accommodate in the state machine. Today we'll do some more examples, starting with what's known as a ring counter. Ring counter is basically a shift operation. It's constructed using a shift register where the output of the shift register is fed back to the input so that the counter goes through different sequences. So we'll design it for 4-bit. And for the case statement, we first need its state machine. Fine. So 4-bit ke liye it will have 4 states, pretty straightforward. And the states would be, let's start from here, second, third, fourth. So if the first count is 1 0 0 0, then next one will be 0 1 0 0, then 0 0 1 0, then 0 0 0 1. That will then again it will start from 1 0 0 0. Fine. I'm keeping it simple in the sense that I'm not using an external input, so the state transitions will be straightforward. If I start from here 1 0 0 0, at the existence of the positive clock edge, it will move the next state, then this, this, and like this, right? So let's try to write a VHDL code for this. Again, it will have a simple entity. There will be some library declarations. Library IEEE. Then within this library, I will define a package. Then we'll define the entity. So entity, let's say ring counter is, then port, you'll only have clock as the input port, and account as the output, std logic vector 3 down to 0. This is my initial state. Okay, then the architecture, we'll have architecture FSM of ring counter is fine. And first of all, we have to define a type, as user defined type. We have been calling it state. Let's stick with that name. And this time it will have 4 values. So again, let's call it 0, 1, 2, 3. Fine. Assume that this is 0, this state is 1, the next one is 2. You can use any name, so it's not, but let's stick to this. Let's state these state names. Then again, as usual, I will define 2 states, 2 signals rather, signal previous state and next state, and I will define these 2 signals of the type state. Right? Then there will be the begin of the architecture. Then since it's a sequential circuit, we'll have to use a process. So start process. In this case, I have only clock as the input, so the sensitivity list will have clock. Then again, the first process will be for the transition that is related to the clock. So in this, I will simply use a if statement for the clock. So if clock event and clock is equal to 1, then previous state is equal to next state. Then I will end if and end this process. Fine. Then I will initiate second process wherein I will use a case statement to define the output in each state and how to move from the current state to the next state. Fine. So again, I will initiate second process. It will have its own begin. Then we'll use the case statement with previous state as the identifier. And then this identifier can take different values starting with zeros. And when the circuit is in the state 0, count has a value of 1000. And the next state is 1. Fine. Similarly, when previous state has a value 1, then count will have a value 0100, and from this state my next state would be 2. Fine. Similarly, when previous state will have a value of 2, then in this state count has a value of 0010, and my next state is going to be state 3. Then when I am in the state 3, count has a value 0001, and my next state will be back to 0. Fine. So we define all the states. We'll end the case statement. We'll end the process. Then we'll end the architecture. Fine. So this will code your ring counter. A modification of a ring counter is a Johnson's counter. So take that as an assignment. You will code a 4-bit Johnson's counter. Fine, because with a normal ring counter that we just designed, you can only have 4 states. Johnson's counter, I think it allows you to have more states, double that of this. You'll just study you must have studied in digital electronics. You need to capture its FSM, then accordingly write a code using the case statement. Fine. So next example that we'll be taking is what's known as a button press synchronizer. It basically synchronizes the pressing of a button to a clock. It's a very important circuit that we use in digital electronics. So as the description, brief description is that it basically is a circuit, a sequential circuit that synchronizes a button to a clock signal. Fine. It is, like I said, when it's a circuit that whenever you press a button, the result is a signal that is high for, maybe I should write it, that is basically just circuit when the button is pressed, the output is high, but this is important for exactly 1 clock. Even if you keep on continuously pressing the button, it will only go high for 1 clock period. Right? Sequential circuits, the behavior of sequential circuits we often show in terms of timing diagrams. Again, something that you must have studied in your basic digital electronics. If you have done a course on system design, some advanced course on digital electronics, you must have studied these. I will not explain that, although it's self-explanatory. So I will have let me have a clock signal here. These are my clock pulses. 1 period, 2nd period, 3rd third, and so on. Fine. And we are interested in these edges, the rising edges. And so for your reference, if I drop the transitions using dotted lines, this is one, second rising edge, third one, fourth one, fifth one, and so on. And then if I have an input, by input I mean the pressing of the button. Let's say I press the button, so actually I am not pressing the button, it is in the release state. So let's say I am pressing the button here and I keep it pressing, let's say up to this instant. Yeah, say up to this instant. Then let's say I release it. Then somewhere, let's say here, I again press it. Fine, so this is my clock. This is my button B that I am pressing. Now the output will be something like this. And the output, I'm assuming that these are made from flip-flops, not latches. So I will be responding only to the edge of the clock, not the level of the clock. Again, something you must have studied in the digital electronics. Okay, so it will be 0 here, positive clock edge, and the button is being pressed. Fine. So as per the description, the output will stay high for exactly 1 clock cycle from here to here. Then even though the button is being still pressed after this, but it will go 0 up to the instant where you first release the button, then again press it, then it will go high. So the behavior is something like this. If you continuously keep on pressing the button, it will be high for only 1 clock cycle. And to again get it high, you will have to first release the button, then press it again. Fine. So let's call this, say, oh, this is, yeah, BI. Yeah, anyways, this is fine. B is the pressing of the button and O is the output. Now we have to capture its state machine, because to use a case statement to code this in VHDL, the first and the foremost step is we have to capture the finite state machine. Fine. So if I come up with an arbitrary state, state A, the initial state, and in this state, let me assume that the output is 0. Fine. Now from this state, two things can happen. I can press the button and I can release the button, the state. So if I don't press the button, I will continue to remain in the same state. So this is the transition for not pressing the button. But if I press the button, then I will have to define a second state. Let's for the time we call it B. So this is for B. And in this state, once I move in this state, my output will be a binary 1. So this is basically corresponding to this. Initially it was released, so output was 0. If I keep it the button released, I will stay in the same state. But if I press it, I will move to the next state wherein my output is 1. Fine. Now in this state, the next state B, if I continue pressing the button, because the behavior of the circuit is you press the button, it will only be high for 1 clock cycle. So this output will be 1 for only 1 clock cycle, irrespective of whether you have released the button or whether you are still pressing the button. But if I continuously press the button, ultimately I will have to define another state, let's say state C, and the transition will be something like this, that if I continue to press the button, I will move to a state C wherein output will again be 0. Fine. But if I release the button at B, at the state B, if I release the button, I will again go to the state where output is 0. Fine. Now you may argue that in state A as well as in state C, the output is 0. Fine. But the problem is you have to take into consideration what happens after that. Look here. I am continuously pressing the button. Output is 0. Fine. So this means for this particular state, जहाँ पे output is 0, my prerequisite is the button is continuously being pressed on. But later on somewhere here, when I again first release the button, then again press it, then it goes high. Fine. So this is basically this one corresponds to state C. This corresponds to state A if I release it. Fine. So this means in my state machine, if I release it after pressing for some time, I will move to state A so that after releasing it, if I again press it, I will move to state B where output is 1. But if I continuously keep it pressing, I will move to state C. And in this state, if I still continue to press it, I will stay in the same state. But somewhere if I release it, then from here, I will come back to state A. Fine. So this is the complete state machine for my button press synchronizer. This is, like I said, the foremost challenge here is to capture the FSM. And your FSM description should be complete. In the sense, for every state that exists in your FSM, you should be able to define the transitions. Fine. So this is the finite state machine. Rest we can easily code it now that it is defined. You will have the first part as the library declarations. You can define it. I will simply put library declarations. Then you will have the entity wherein, let's call it button press synchronizer. You will have some port definitions. You will define clock. You will define the input B of the type STD logic. Then you will have output O. Mode will be out. Type will be STD logic. Then we will end our entity. Then again, we'll initiate an architecture. FSM of button press synchronizer is. And within this architecture, I will define a user defined data type. Type state is, let's stick to 0, 1, 2. You can use in names. Yeah, let's use this time round A, B, C. Fine. Then we define two signals. Rest it is just a template. We are, as far as the coding is concerned, we are using the same template over and over again. Fine. And then we'll begin. Then I'll initiate a process for the clock. Begin if clock event and clock is equivalent to 1. Then we will have the clock transition. We'll end our if and we'll end the process. Then we'll initiate the second process wherein we will be using the case statement. That is the main process. So I would initiate another process with previous state and the input B as the sensitivity list. Begin, and here is where we use the case. Previous state is, then we will define different values for this case. When 0, then in that case my output is 0. Use this, and then I have to define how I can move the next state. So if B is equivalent to 1, then next state, okay, we don't have 0 here, we had used A. Okay, so next state will be then B. Fine. And else you will continue in the same state. So next state still will be A. And if Then when you are in B, your output is 1. And if B is equivalent to 1, then your next state will be state C. Fine. Else, you will continue in the same state. Is it? Just a second. Let's have a look at the FSM. Okay, you'll have to come back to A. Okay. The next state will be A. Fine. Then we will end if, and then for the final value when C, then output will again be 0. And if B is equivalent to 0, then your next state is going to be the initial state A, else you will continue in the same state. Right? Then we will end our if, we will end the case, we will end the process, and we will end our architecture. Fine, so this will code a button press synchronizer. Fine. Now, this kind of a design, the way I have captured here, is known as a Moore design. I told you that a state machine can be captured as a Moore machine or a Mealy machine. Now, in a Moore design, the output in a state, so in the Moore design, the output depends only on the present state. Fine. So if you are in a particular state and the machine is a Moore machine, you are in that state, so output is defined. Like in this case, if you are in state A, output is 0, regardless of what the input B, what the value of the input B is. Similarly, if you are in the state B, your output is 1. You're in the state C, your output will be 0, regardless of what the value of B is. But you can also capture the same behavior using a Mealy machine. And in a Mealy design, in a Mealy design, the output, it depends on two things. First, it depends on the present state, which is the same as in the Moore machine, but it also depends upon the value of the input's present state and the present inputs. Fine. Generally, if you are capturing your FSM as a Moore machine, the machine is simpler, but it will have more number of states. Fine. But if you are able to capture it a Mealy machine, you may be able to save some states. Fine. For example, if I continue the same thing here, if I capture the button press synchronizer, the description we had here as a Mealy machine, and if I start with the state, let's say state A, which is my initial state, where I define output. Now I can define the output here because it is a Mealy machine. Output will be conditional. So it will depend is state mein what my input is going to be. So it will be, we typically show it something like this. If I don't press the button corresponding to this, then my output, we show it something like this, will be a binary 0. And I have to continue to stay in the same state. Fine. But if I press the button, so maybe I'll have to initiate another state. If I press the button, we had used, I think we had only used B. If I press the button, then my output will be 1 and I will move to the next state B. Right? So here output is conditional. It depends upon what the value of the input B is. Right? Now in the state B, if I continue pressing the button, so something like this, my output will be 0. and I will stay in the same state. But if I release the button, output will still be same, but I will move back to the state A from wherein I can restart. Now this is a Mealy machine. This is a Mealy design. And as you can see, if you capture this as a Mealy machine, you are actually preserving one state. Fine. Now, then you can actually translate this into a VHDL code. You will define a state which type, a new user defined type says state, which will only have two values, A and B. Then as usual, you will define previous state, next state, then first process will define the clock transitions. And in the second process, you will use a case statement. So what I will show here is the second process. So I'll have process again as a sensitivity list. It will have previous state and it will have the input B as a sensitivity list. Then we will begin and we will initiate a case statement. So case previous state is, so first value, it only has two values this time around. So when A is equal to 0. Now you can't specify the output. Fine. In the previous case, we were in the state A, so it was implied in this state output is going to be 0. But here the output is conditional. It actually depends upon the value of B. So when A, then I have to put the condition that if B is equal to 0, then my output will be equivalent to 0. And simultaneously, I will define my next state will be the same as my current state. Else, my output will be what, 1, and my next state will be the state B. And if this is for the first value of the identifier previous state corresponding to state A in my FSM. Then let me continue it here. When B, again, we'll have to check if input B is equivalent to 1, then output is equivalent to 0, and my next state, it actually is the same state B. Else, output will still be equivalent to 0, but my next state will be the state A. Fine. Then I will end if and the process and the case rather. Then end the process. Then you will end your main architecture. Fine. So whenever you have a sequential circuit, you can capture its behavior as a state, as a Moore machine, or as a Mealy machine. Mealy machines are usually difficult to capture in this sense because it is a kind of a conditional output. In a particular state, what your output is, that depends upon the input. So Moore machines are simple, but you may have some extra states to take care of. Fine. We'll stop here and I may post one more video about finite state machines, wherein we can work out some more examples, some more applications of the finite state machine and the case statement in VHDL. I'll stop here.